Good morning, everyone. Today is our first unsupervised learning lecture on clustering. It's the first of two. We have two unsupervised learning lectures, one on clustering and the other on dimensionality reduction. They are the two main types of unsupervised learning, and they are the two types that we will look at in the course. There are a couple of others which are, let's say, a little bit less present in usual machine learning pipelines, but clustering and dimensionality reduction are the most common ones, and probably will slowly become an important part of your let's say tool set of the machine learning pipelines that you build on the future. So this is, well, as always, you can ask questions whenever you want. I will not interrupt the slides all the time for questions, but I will be looking at the chat. You can also raise your hands using the Zoom functions, and then after from between every couple of minutes, I will look and try to answer questions as they come. So I don't know how many of you have actually heard about unsupervised learning or know what it is. Probably you've heard the word clustering or dimensionality reduction floating around in any way, but I'm not sure if you understand what it means to that these things are unsupervised learning instead of supervised. But basically everything you've seen so far in the course, as far as I remember, was about supervised learning. So it was either regression or classification problems, which means that there is, in all cases so far, there was always a response variable that you want to predict or that you want to model after that, right? So you actually have, let's say, how can I put this? You have like a cheat sheet of things like, I know these things are true for this data set, and I want to train my model in whatever way that you've learned so far, such that if I come up with new data that's not the training data set that I have right now, then I can predict these response variables for the new data. And whether it's regression or classification, actually, if you think about it, even though the algorithms are different, actually, conceptually, they're very similar. The only difference is that for regression, the response variable is continuous, right? It can take any values in a certain interval. And it could be even like minus infinity to negative infinity to positive infinity, but usually within a certain interval. And then it can take any value. So that's a continuous variable, a response variable, and that's why it's called, that's when it's called regression. And the classification is more or less the same. The only difference is that it's a discrete response variable. So it only takes a specific, not a specific number of values. It could also be infinite in case of the natural numbers or so. But usually it's not. Usually it's a response variable that has a finite number of values, and they are discrete. So it's either class A or it's class B or it's class C, right? But in both cases, you're trying to predict a certain response variable that you have, that you know, it's like a known fact about the data set, and then you want to predict that the same thing for future data that you may get that is not part of your training, right? So that's when you train the model. So you train the model to do this part here, this prediction here, that goes from X to Y. For unsupervised learning, we don't have these response variables. We just have the data. And that's why it's called unsupervised, let's say. So you can think of your supervising, like your machine learning model is being supervised by you, because you're telling them the model what's right and what's wrong, right? So like for example, this specific data vector or observation is of class B. So I'm supervising the model. I'm telling him, look, you should predict class B. If you don't predict class B, then you're wrong. And if you predict a class B, then you're right. So you're supervising the training process by telling the model what's right and what's wrong, because you have that information. When it's unsupervised, basically the model is on its own. So there is no way for you to say what's right or wrong. And that's the main difference between supervised and unsupervised that comes from the name itself. It's you don't have a response variable, and by not having a response variable, you cannot tell the model what's right and what's wrong. Even though, of course, in regression problems, you don't necessarily know the values. I mean, you know the values, but it's a little bit harder, of course, to determine error. But you can still do it. It's only continuous. In unsupervised learning, there is no response variable. Okay, so the problem that we're doing is not a prediction problem. The problem that we're trying to solve is not a prediction problem. It's not a matter of predicting something that will come later. It's a matter of actually finding patterns in the data for a variety of reasons. So there are varieties of patterns that you could find in the data set. And even after you find them, the goals of how you use them can be for many, many different reasons, right? So we say that with unsupervised learning, actually, your goal is to train your model to discover patterns in your data set, groups. So you may have groups, you may have very salient groups in your data set, even though you may not have a specific setting of classes. Like, I don't know what is class A, I don't know what's class B, and I don't know what's class C. I have no idea. But by using unsupervised learning, you may find out that there are actually very clear, for example, as an example, there are 3 groups of data points in your data set. Even though you don't know what are you don't know what the classes are, you don't know why they are exactly why they are grouped together in terms of the conceptual meaning of the data set, but you can find them anyway, right? So so this is usually the most common, actually the one that we're going to deal with today. But that's not the only thing you want to find out. You want to find out other things like subspaces or manifolds, and these are a little bit more complex, but it's also about finding these structures. In a way, you could think of them as structures, even though when we think of structures, we think of 3-dimensional space. But actually, mathematically speaking, you can define structures in a way that doesn't matter if you're in 3D or in 4D or in 100D or whatever. There are concepts that describe patterns in a way that doesn't really matter the dimensionality of your data set. But so basically, in a nutshell, it's about finding out patterns in your data set that are not random. So they can be detected, even if you don't know the classes, or you don't have any regression or response variable or anything like that. Okay, so conceptually, this is what unsupervised learning is. So what happens is that since we don't have these kinds of response variables, then unsupervised learning is a little bit challenging, because then you have to really be creative to come up with these ways to do things. Of course, I'm not saying that unsupervised supervised learning is not challenging. Of course, it's challenging. It's very challenging also to be able to build good classifiers or good regressors, let's say. It's also challenging, but the unsupervised learning is challenging in a different way, because when you have a classification problem or a regression problem, and you have this means of determining error in a very clear way, so to speak, because you have the exact response variable that you want to predict, then you can optimize it in a much more straightforward manner, in a way. I don't want to, I'm trying to be careful here not to say that unsupervised learning is harder than supervised learning, because you cannot measure that, what is harder than the other. It's just that they're challenging in different ways, right? Because when you have supervised learning, you can optimize towards that. That's the whole idea of optimization. You need to have a goal that you're optimizing for, right? A clear goal. And then you can do a million different ways. You can run so many different optimization algorithms, but it starts from the fact that you have a goal, a clear goal that you want to optimize for. With unsupervised learning, we also do optimization, because machine learning and optimization are 2 things that go very much hand to hand. However, there is no simple, straightforward goal. as we have with supervised learning. So we come up with the goals ourselves instead of having a predefined goal as a response variable. So we must come up with creative, interesting goals to optimize for, and then optimize for that. And then you have a certain result, like, oh, I want to optimize the separation of the points. So I come up with this goal, and then I optimize for it, and then I find out the clusters, for example. But this goal of like how to define separation of points, that's something you must come up with. It's not a straightforward thing that comes with data, right? And again, exactly for the same reason, it's hard to assess the results. Because again, when you have supervised learning, you have a response variable, so you can tell what is the error. Like the error is basically how much I'm deviating from the expected response that I have. It's predefined. But with unsupervised learning, you don't have that goal. So you don't have that. So it's, even if you do define your own goal, like, yeah, I defined it that I want to, separate between, maximize the separation between the points of two clusters, so on and so forth. Still, when you assess those results, they're subjective because they came from an optimization goal that you defined yourself. They don't come from let's say, a real world definition of what is right and wrong. So for example, if you're classifying between cats and dogs, then you have a way to assess these results that is quite straightforward. Well, if a cat is classified as a dog, then that's wrong, right? You know it because you know what's a cat and you know what's a dog. So it's very easy to, it's very right. I Sotirios, could you mute your microphone, please? Well, I think I can mute his microphone, actually. Yeah, oh, okay, I can, good. So, as I was saying, I said it was easy, but that's because I was distracted. It's not easy. The supervised learning is not easy. That's why I'm trying to be very careful with that. But again, when you're talking about supervised learning, there is like this external measurement of error that comes from real life. Again, just so we get back to the example, if I'm trying to classify cats and dogs and a dog is classified as a cat, I know that's an error because I know what's a cat and I know what's a dog, so I can define that. But when you define some kind of a clustering goal that says I want to maximize separation between points, there's always this subjective idea of what is really a good separation between points. There are many ways to define that, especially when you're in high dimensional spaces. Of course, if you're looking at something in a picture, then you can more or less say, yeah, I know what's a good separation. But the truth is that actually we don't really know that clearly, especially, for example, if you look at the picture on the right side, you can see that there are clusters separated in different colors. But just imagine, what if there were no colors in this picture? What if I didn't give you these colors? Would you really be able to separate this cluster from this one, for example, the green one from the pink one? Or let's say the light blue one from the green one? Because the light blue is broken into two pieces here, and there's a green one in between. Like, would you be able to visually determine that these two clusters are different, or would you just count them as being one? So that's why this separation is not super clear, even though we find ways to define it as being a little bit clearer, but the truth is that inherently it's subjective. Okay, so there is no cross validation. You don't cross validate with unsupervised learning, exactly because you don't have these very clear. I mean, if you come up with some clear goal, you might do that, but still it's not really that simple. So basically we don't do cross-validation, and there's no true answer to check, again, as with the cats and dogs example. And the exploratory data analysis is the main, let's say, application for this. It's when you really like, I have no idea what this data set is about, so I want to explore it. I want to see what I can find about it, even if I don't have a response variable. Or maybe you do have a response variable. Actually, I think most of the time you do have a response variable, but still you want to set that aside for a second and look at the data as for what it is, without really looking for the, without really like considering the response variable for a while, then, you know, let's just look at the data. What is in it? Do we have clear clusters? Can we see some kind of a trend in terms of correlations of features and things like that? So all these things that are unsupervised and don't relate to the response variable itself, you can do that, and then you can have this exploratory data analysis of your data even before you consider the response to do whatever you want to do. It's probably the main application, but there are others. Yeah. Okay, so as I said in the first slide, there are two main types. They're not the same, but they're in the main types of unsupervised learning, clustering and dimensionality reduction. As with classification and regression, they are also similar in many ways. Only one is more discrete and the other one is more continuous. So you will see that later, but we will start with clustering because I think clustering is the most straightforward, the one that comes to mind more easily and it's easier, a little bit easier to define. So we start with clustering. Then next week we go to dimensionality reduction, which happens to be my area of research. So most, if not all, my research deals with dimensionality reduction in many different ways. And I just want to take this opportunity also to tell you guys that if this is something that it looks interesting to you and that you feel like it's something you would like to do, for example, in a thesis, then you can come talk to me, and we can find some interesting topic for you to work on your thesis related to clustering and dimensionality reduction, and maybe even supervised learning, but not mainly on supervised learning, because I don't do research mainly on supervised learning. So we could mix and match a little bit, then we can get another supervisor, for example, Yunus, who does work more with supervised learning. But anyway, I just wanted to take this opportunity to tell you, if this looks interesting and it's something that you would like to do, you can come talk to me. I have basically like a stack of ideas that you could do in your thesis, okay? So clustering, let's start with clustering. Basically, in a very coarse overview, clustering comprises techniques for finding subgroups in a data set. So after you apply a certain clustering technique to a data set, the result is that each element usually belongs to one and only one cluster. This is the case that we're going to treat today in the lecture because it's the most common one. Of course, there are fuzzy clustering techniques out there that will give you like a probability that a data set is part of a specific cluster or another. And in many ways, maybe that is even more accurate because you know, if you think about clustering in general, it's a very rough simplification of reality. You know, you don't necessarily, when you have a data set, not necessarily every element of that data set is very sharply in a cluster and not in another cluster, right? I mean, depending on different perspectives, you could have different results. But in general, in order for an element to be in a cluster, the element must be similar to other elements in the same cluster. So when you take this collection of points that comprise a cluster, they should be similar. In any definition of clustering, even though similar could be defined in many different ways, clustering could be defined in many different ways. But I think overall, if you for every clustering technique, the elements in a cluster are supposed to be similar to each other, and they are supposed to be different to elements of other clusters. That sounds obvious, right? But it's an interesting definition to think about, because what does it really mean to be similar or to be different? Maybe when we think about these concepts, maybe they come as obvious, but they are actually not obvious. So for example, this is a very classic example that I'm using in the lecture. So we have some characters from the Simpsons cartoon, and then you apply some clustering, right? And maybe one clustering algorithm will say, well, I'm separating between the Simpsons and the not Simpsons. So I have Marge, Homer, Bart in one group, and then I have the other guys, which I don't remember the name, in the other groups that are not Simpsons. that sounds like a perfectly fine way to separate these characters into two groups. And I define that I want two groups, right? In this sense, just so we can play with this idea. But it also could be separated into male and female. That would also be a very fine, normal, let's say, standard way of separating these characters, and that it wouldn't be no problem with that. Because okay, actually, I think it's more salient, the separation between male and female. So maybe different people might have separated these characters into different groups, and it's the same with different clustering algorithms, because different clustering algorithms will look at different perspectives of the data in order to define similarity. So the one in the left defines similarity by family relationships between the Simpsons and not Simpsons. That was the similarity that the algorithm focused on, while the other focused on gender. So when you have high dimensional data, when you have hundreds, maybe thousands of dimensions for each element of your data set, then these perspectives will happen. These different perspectives will happen because you have too many features, and you can't simply just say this is just, there's just one group and that's it. Well, most of the time for complex data sets. Maybe a simple data set you can do that, but for complex data sets with many dimensions, these different kind of definitions of similarity, they come unfortunately, and it makes things harder, but that's how it is. In this case, for example, you could consider that each of these characters have, I don't know, like two dimensions. One is Simpsons, whether it's a Simpson or not Simpson, and the other one is gender. And then each clustering algorithm that happened to choose one of these two features to focus on. So which one's the right one? It's hard to say. And like I said, different clustering algorithms will do different things, and there are many. I mean, this one is just a picture that I got from reference number 3. You can look at it at the end of the slides. But this is just this is not even 1% of the techniques that are out there. I mean, there's a lot of techniques. It's the same with supervised learning. You also find a lot of different algorithms that classify things in different ways, right? You might think, well, what, if two algorithms are very good, then they should, why would they perform differently? But that's just how it is. So clustering is the same. You have different algorithms that perform in very different ways, and will partition your data set in completely different ways. Of course, some data sets, like I said, some data sets are a little bit simpler, and they have very clear structures in them. In those cases, probably different clustering algorithms will kind of have the same results. At the end of this lecture, I'm going to show like an overview, a comparison, and then you will see more or less how different algorithms behave differently. So if it's a simple data set with simple structures, they may behave the same, but for complex ones, no. Okay. And it usually has this main branching between hierarchical and partitional data set algorithms. And anyway, there's a lot of, I just showing this as an example of how many techniques are out there, but of course I'm not gonna focus on this. In this lecture, we're gonna look at 3 different clustering algorithms, and I will go over them and explain to you the conceptual background and how, more or less, how it works, the intuition behind them. Not a lot of math. You can go deeper into the math later if you want, if you want to learn a specific algorithm. But I just want to make sure you have a good overview of the intuition between the main classes of clustering algorithms. Okay. And we start with K-means, which is probably the most common clustering method, and maybe the most straightforward. I'm not sure, but I guess it's also it's gonna sound familiar to you because it has a little bit to do with k-nearest neighbors and things like that. So K-means, as with many other clustering methods, partitions the elements into predefined number of clusters. Most clustering methods that you're going to find out there will require you to determine how many clusters you want. Okay, Some of them find out an optimal number for you, even though finding out the optimal numbers, it's a completely different optimization process also that can also have its own problems. But some of them do. And some of them will basically generate every possible clustering between 1 and n, and then you can choose which one you want, right? But in this case, for K-means partitions the elements into predefined number of clusters. So that's why it's called K-means, because it's a K number of clusters. And the goal of K-means is to minimize the intercluster variance. So the minimization here is not just in the name, it's actually, it has this kind of a optimization process built in, and I'm gonna try to show you how it works. And a simple example that I took from, not from the Géron book, from another book that is also freely available, and it's in the references, so you guys can also take a look at that later if you want. But a simple example is this. So you can see this data set here on the right, on the left, and you can see there are no colors here, right? So this is a little bit like what I said in the beginning. Maybe if you look at the results with colors, then you say, oh, it's obvious that this is the separation between clusters. But actually, when you look at them without colors, then maybe, is it really that obvious? So so this is the data set. And then you apply K-means with K equals 2, and then you get 2 results here. You have one big cluster here and another bigger cluster over here, right? And it's interesting to look at as we go for K equals 3. Then the colors themselves doesn't matter, right? I guess you understand that it's just different colors to separate the clusters. Doesn't matter that one is blue and here it's blue and here it's green. I mean, it doesn't matter. It's just what matters that they're different. But it's interesting, for example, that, well, we go from K to K equals 3, and this cluster here was actually broken down into 2 different clusters, while this basically stays the same. Yeah, it's exactly the same actually in this case. And then as we go to K equals 4, it still remains as more or less, not exactly in this case, because then these points on the borderline here, they jumped off to another cluster, but most of it stays the same. So it's interesting to see, like, for example, this is one thing that you could have in your exploratory data analysis, that, you know, even if you break the data set down into more clusters, this cluster remains the same. So apparently, you know, it's not a statistical validation or anything, but apparently in an exploratory data analysis perspective, it seems to be a very cohesive cluster. And then as you can see, you break down and slowly, I guess, for example, if you look at K equals 2, it's like, yeah, okay, this is quite an obvious partition into 2 clusters. It's very clear that there are at least 2 clusters in this data set. Then when you break them into 3s, yeah, I mean, it's not bad. I can see that it's not bad, but I mean, it's still, you know, if you look at this borderline over here, like, is it really that easy to say which cluster these guys are part of? Wow, this is a bad one. So is it really that clear which clusters these guys are part of? Like, are they really part of the blue one? Or if I assign them to the orange one, would that be a disaster? I'm not sure. Probably not. So then you can see how it becomes a little bit subjective, the whole thing, because there's some points, and probably the points here and the points here, you can say, yeah, well, they're part of different clusters for sure. But as it goes, as the clusters become, let's say, more entangled, then it starts to become maybe, well, you know, not sure. But you forced the algorithm to have 3 clusters, so the algorithm will have 3 clusters because you define K equals 3. And there will be 3 clusters no matter what. Whether it's representative or not, it's hard to say. And then when you go to K equals 4, this problem becomes even worse, right? Then you can say, well, you know, this cluster here, this orange cluster here, like, what's the point of this? These guys and these guys are still more or less the same as they were before. You can see that, not exactly, but they have very similar clustering assignments here. But the orange one, it feels forced, right? It feels like you forced the algorithm to create 4 clusters, and then it tries to like, okay, I'm gonna do my best to come up with 4 clusters, but I'm not sure if these are actually, you know, right. So, but the algorithm will do that anyway. And if you ask for 10 clusters, it will give you 10 clusters. Then probably gonna partition some of these other clusters, maybe even this one, into smaller parts, because that's, you know, well, you want 10 clusters, I'll give you 10 clusters. So what's the algorithm behind this? Let's take a quick look at this. Of course, this is not going to be like a super mathematical treatment of the whole thing, but it's just supposed to give you an intuition. Okay. So the first thing we do is, the algorithm is, we start with random clusters. So every element is included in a cluster K randomly. So let's say, okay, I want 3 clusters. Okay, no problem. I create 3 clusters, so to speak, but then I just assign points randomly to these 3 clusters because I have no idea, right? It's the first step of the optimization. So as with many other algorithms that you may have seen before in the course, we start with a random solution, and then slowly we improve the random solution until we get a good solution at the end. So the important step here is the improvement of the solutions from step to step, right? And then we start with a random one because that's all we have. We don't, I mean, we have no idea how to do better than that. Let me see if that's, yeah, that's step number 1. So you can see here, step number 1, every point has a different color, but they're all basically just random. There are no patterns here. Then what we do is, for second step, compute the centroid for each cluster. The centroid is the vector formed by the means of each feature. So in this case here, this data set has 2 features, right? Because that's what we're looking at in the pictures, just X and Y. They're just 2D points. That's just for simplicity, right? Or else how could we visualize this? It's gonna be much harder to visualize. So in this case, basically you take the X and the Y of every point in a cluster, and you take the mean. And not surprisingly, the centroids end up being in the middle because, you know, it's random, so there are points everywhere, and the means are going to be near the center of these, both in the X and in the Y coordinates. That's not surprising. That's actually that's what should happen because it's random. The clusters are randomly assigned, so that's what you expect. Then what you do is you reassign the clusters of every element in the data set such that each element is in the cluster with the nearest centroid. So now we're going to take this centroids that we have here, then we're going to go over every point, and we're going to ask which centroid that I computed in the previous step is the closest to me right now. Oh, for the points that are over here, it's the orange centroid, because as you can see, randomly, the orange centroid is sticking up here a little bit. It sticks up to this, up and to the left. So all the points that are around this area over here, they are going to be orange, right? So yeah, well, oh my God, I can't see this. So all these points over here, they're gonna be assigned to the orange point because they are the closest to this. Oh, that's horrible. To this centroid over here. Let's try the next one so that I can try to make it a little bit more interesting. And then you have these, let's say there's pinkish points here, and they happen to be closer to the red centroid, which is sticking out to this side over here. Randomly, again, because the initial step was random, right? So randomly, it just happened that this pink, magenta, I don't know, point was sticking a little bit down to the left. So all these points were assigned to that. And the same thing for the green ones. And now, after we did this, we go back to step 2 and repeat until the clusters do not change anymore. So what's step 2? Compute the centroid for each cluster. And now when we do that, voila, that looks much more interesting than before, because we basically took, again, all the points with their own cluster assignments. We recomputed their centroids. So now, of course, you know, the centroid for this guy over here, I'm gonna use another color again. yeah, I'm gonna just use black just as an example. So now you see the centroid of this guys over here is this one, because if you take the x, all the x-axis, all the x, let's say, values and all the y values, this is the center of the cluster. And again, for the same for the pink, the same for the green one. So now we see that, you know, it's makes much more sense. And then we go again and again, we reassign the clusters of every element in the data set such that the element is in the cluster with the nearest centroid. And you may think, well, you know, well, but why would you do that? Because, you know, the centroids already make sense. Well, mostly, but not exactly. Like, for example, if you look over here, then you can see that, yeah, for example, these 2 points over here, they were yellow in the previous one because of this assignment step here. But when we reassigned the clusters, they became green because they are closer to the green centroid than to the yellow centroid. And there are some other points over here also that where the same happened, like these guys over here. You see that they became green here, so you can see that they became green. I'm drawing with the horrible mouse. So yeah, but anyway, so they were reassigned. And then after we did this, we go back to step 2, and then we compute again, we do it again, and then we do it again. And then at some point, you will go to steps 2, 3, and 4, and nothing will change. The centroids will be the same, the cluster assignments will be the same, because that's it. You've optimized it. And that's when you stop, usually, with K-means. Of course, there are implementations where something's tweaked a little bit here and there, and then it never actually happens. So some implementations will actually limit the number of attempts or something. But usually that's how it goes. And this is a more mathematical description of the thing that I just described to you. It's a more concrete, objective definition other than the actual intuition that I gave. So CK is a set of points I, such that X, well, set of, let's say, numbers I, such that Xi, so the ith point is in cluster K. So there are 3 different sets, well, not 3, K different sets of points. You know, to be very precise, the union between these points equals the set of all values. So the union between these clusters equals the set of all available points from 1 to n, and the intersection between these sets of points, which are the clusters, is empty if k is different than k. So of course, if it's basically, if you look at 2 different clusters, they have no overlap, and every point is in a cluster. So there are no points left out of clusters, and there are no points in 2 clusters at the same time. Basically, that's what it says. So if you consider that, then formally, the K-means algorithm is the minimization of this cost function over here, okay? And this cost function over here basically is saying that the intra-cluster distances, which are xi minus xj, you know, how do you say this? The norm of xi minus xj squared, the sum of these internal norms between the points must be minimized, because these, and then you sum all, after you sum the actual intra-cluster distances, let's say, then you sum all the distances of all the clusters, and that should be minimal. In this case, you can see that there's no, we're not checking distance of points between clusters, right? So a point from one cluster and a point from another cluster, that is not minimized in this. Let's say you might consider that as implicitly minimized because of the entire definition of the formula, but still, and it's not explicitly determined. So basically, it's just for 2 points that belong to the same cluster, we sum for every 2 points that belong in the same cluster, we sum their norm. Then we take so this is, let's say, like the average, right? Or not really the average, because this is a pairwise thing. But anyway, you divide by the number of elements in the cluster, and then you sum this result that you get for all clusters, and that should be minimal. So basically, minimized intra-cluster variance between the clusters. And the fact that you are giving the k, you're saying I want k equals 3, or I want k equals 4, or I want k equals 5, makes it so that this can actually be minimized. If not, then it would be a little bit harder, because then basically you would put every point in their own cluster. I guess that would probably minimize. I'm not sure by head, but either that or the other extreme, or every point's in the same cluster. So the fact that you're, again, the fact that you're defining the k yourself, you give it like I want k equals 3, that makes it possible to minimize this. But the actual let's say minimization that you're doing is this like procedure of reassigning cluster centroids and recomputing the centroids and so on and so forth. This iterative process. This is the minimization of the cost function. And again, just to connect back to what we had in the beginning of the lecture, you can see that this cost function over here is not something that comes from the outside. How can I say? It's not something that comes from a real world perspective or of what I want to have in the clusters. As you can see, this is just a mathematical formula that someone came up with a long time ago, which unfortunately I don't remember who was the person who proposed K-means in the first place. Probably a long time ago. But this is just a mathematical formula that someone came up with and said, yeah, you know what? I guess that this would be a good goal to optimize for if I wanted to have clusters, or if I want to partition my data set into a specific number of clusters. Is that the best one? Probably not. I mean, it's a very common, is it a good one? Yes, it's a perfectly fine one. Is it the only one? Obviously no, because we have other clustering algorithms that have other different goals. Is it the best one? Probably not. We've learned after decades that there are many other clustering algorithms that will work much better in many situations. Maybe it's a very good one for a specific set of data sets, but certainly not for every data set possible, right? So, but anyway, it's just a mathematical formula that someone came up with. It worked, and some other people have come up with other formulas, and they're all basically just, let's say, just conjectures, and there's no way to actually determine the final best one. If and it's interesting to think that in theory, if we didn't go through this optimization that I showed you a couple of slides ago, of reassigning cluster centroids and so on, if we didn't do that, and we wanted to brute force, let's say, to say I want to find out the best possible cluster assignment period without any doubt, then you would need to do k to the nth power operations in order to actually check for sure, brute force the whole thing and say I want to find the best possible clustering, and then I would have to search the entire solution space of every possible clustering, and that would involve k to the nth power operations, which is absolutely unfeasible for anything that's not basically, like, I don't know, have a couple of a couple of points. The n is like 10 or 20 or something. I don't know, not even that probably. So it's not feasible, and that's why we went through the algorithm that I explained, which is one optimization procedure. And as you've seen in probably in other algorithms, supervised ones, an optimization is usually a search for a local optimum. It's a search for a good solution that hopefully is close to the final final possible best solution period. But it's never guaranteed to be the one that gives you the best result. So as we've seen, at every iteration, we improve the solution a little bit. We start with a random one, then we improve until there's no way to improve it, to easily improve it anymore, then we stop. And then we found a local optimum, which is kind of like, yeah, well, it's a good enough solution that we have so far, and we hope it's good. And as you can see, as you've seen before, every new solution is based on the previous one, right? So it starts with a random one, then we have a little bit better one, then another one that's a little bit better, and so on. So finally, of course, the final solution is based on the initial one. So if the initial one changes, the final one also changes. Well, sometimes you find the same local optimum with different initial guesses. But in general, a different initial guess will give you a different final solution, which is perfectly fine because complex problems usually have many different possible solutions that are a little bit better or worse than the other. This is an example of running K-means with 6 different initial guesses. And you can see, well, the cost here is the sum of squared errors. So it's basically that thing we were attempting to minimize, which is the intra-cluster variance, without these that extra term that was here. For some reason, I don't know exactly why in this book they didn't put that, but it wouldn't make any difference because that's just 1 over, you know, the number of points in a cluster. So it's basically more or less the same. The best solution is found 4 times with 235.8, which doesn't mean anything by itself, but it's possible to compare it to other solutions. So for example, the first solution here had a cost of 320, and the final solution here had a cost of 310, so they were not good. And this solution here, these 4 solutions here are exactly identical. They have the exact same cost of 235.8. And they all came from different initial guesses. So it's interesting that for this data set, even if you start with a different random assignment, you usually end up with the same final solution because it's a very simple data set anyway. And then you could, maybe if you were running K-means and you were thinking, well, you know, maybe you run it once and then you get this. And you say, well, you know what? Is this the right one? I'm not sure. It doesn't even look very good when you look at it. There's a green cluster over here that makes no sense. So you look at it and say, I don't really trust it. I'm not sure this is correct. So you know what? Just run it a couple more times. Unless it's prohibitively slow, then just run it a couple more times and look at the whole thing, and then you can choose which one's the best for you. And it's perfectly normal to end up with a local optimum that's not really that good. It happens. So then you try it a couple more times and maybe choose a solution that happens more times, or you know, the one with the smallest costs maybe. There's a simulation here that's very interesting, and actually I'm not sure if you're actually you're not gonna see it now, but I will change the sharing of the screen to see if you can actually see it. Desktop number 2, yeah. Can you see this? Can you guys just quickly let me know if you're seeing this visualizing K-means clustering, this web browser? Yeah, okay. So this is a simulation of K-means clustering. As you can see, this is an artificial data set where you have clearly 3 clusters. Actually, you know what? I'm going to just refresh this. Yeah, okay. Yeah, let's go with this one. So you see, it's an artificial data set that has 3 clusters. Obviously for us human beings who are looking at the picture, and we can see that there are 3 clusters, but there's also a lot of noise just spread around the whole thing. It's how do you say, on purpose. And now, basically the algorithm is to repeat these 2 steps until convergence. So find the closest centroid. And one thing that you may see here is that this was a little bit, the random initialization was a little bit different than what we discussed. It's perfectly fine. It's just that instead of assigning random clusters to every point and then finding the centroids, they just basically threw around 3 centroids in the picture. 3 random centroids, which is perfectly fine. I mean, the initial guess is random anyway. So whether you assign each a cluster to each point and then find the centroids, or just find random centroids directly, they're random anyway. Okay, so basically we started with 3 random centroids, then we found the closest centroid to each point. So you can see that, you know, all the orange points are assigned to this one, all the blue here is assigned to this one, all the green ones assigned to this one. And of course, this initial solution is bad because this cluster here is partitioned in the middle. This cluster here is also has like points, most are green, but some points are orange and blue. So it's a bad solution. Now let's update the centroids. Updating the centroids moves them again to the average X and Y position of every point of the cluster itself. And it's interesting that the green one ended up being over here. And I guess it's because, yeah, it's because of there, yeah, it's because there are so many points over here that the density actually pulls the centroid over there. And now I find the closest centroid again. So you see, we reassigned the centroids, and now it looks relatively, you know, actually much better than it looked before. All the clusters are actually already look right. Update the centroids again. Now the centroids have moved much closer to the center of the clusters. They will never be exactly in the center because of the noise. So the noise also pulls the centroids to other areas. Then find the closest centroid again, update the centroid, and so on. And then you can keep doing this. And you see, I clicked on it a few times, and now it's not changing anymore. If you look down here, it doesn't change anymore. So that means we have converged. And you can keep doing that. So every time I refresh, there's a new data, then I can just keep doing it. And oh, that's interesting. You see, this was a bad solution, and that's exactly what I wanted. Due to a bad initial guess, we ended up with a bad solution, because in the initial guess, the points, this centroid over here happens to be very close to these 2 clusters, and the other 2 centroids happen to be very far from them. So we found this cluster, but these 2 clusters ended up being assigned to the same centroid, because we ended up falling into a bad path in the optimization process. And that can happen. And that's why it's always good to, you know, try again. So for example, I will have the same data, but I generated new centroids now, and I'm going to optimize them again. And now this time we found a good solution, because randomly the initial guess was better this time. Okay. What can I say? It's hard. It's not something that there's no true solution for that problem. It's just every optimization that starts with random guessing has that problem. Do you guys see the slides again, just to make sure? Can you let me know very quickly? But only the slides, right? Not the presentation view. Is that correct? Yes. Okay, good. One thing that you might be thinking is, how can I choose the number of clusters that I want? Well, it's hard. So the number of clusters is the most important parameter. And I mean, is there a way to define that? It is very hard. One way to choose case with what we call this elbow method, which is basically we say, okay, let's try all possible case, or not all, but a number of case from 1. Well, 1 doesn't make a lot of sense, but let's say we start with 1 and until 10, for example. We just try different ones and then run the algorithm with all of them. And then you plot the cost of each of them. So the cost of 1 cluster was very high. The cost with 2 clusters was a little bit high. The cost with 3 clusters was already a little bit low, and then so on and so forth. And as you can see, the cost will always go down, and that's why I told you that if you don't give the algorithm the specific number of K that you want, the algorithm will, if you say, okay, hey, you can choose the K, right? Then the algorithm will always go towards having 1 point in per cluster, because as you can see, when K goes, when you have higher Ks, the cost will always go down, period. That's just how it goes. So that's why you have to give it a specific number of clusters, or else it will just optimize towards k equals n, right? But the elbow method basically will say, okay, you know what? 3 seems to be a good number, because when you go from 1 to 2 and 1 to 3, there's a very sharp drop in cost, which is good because you want lower cost. But from 3 to 4 and from 4 to 5, actually the drop in the cost becomes lower. Like the cost doesn't drop that much anymore. So it could be that 3 is what we call like an elbow of the graph. You know, if you don't know what an elbow, this is an elbow. So this is like there's an arm here, and this is the elbow, and it's kind of like, yeah, you know, maybe 3 is a good number. But that's not always clear. Like, for example, if you look in this example here, maybe you could say that the elbow is here in 2, maybe in 3, maybe in 4. I don't know. It's very smooth. So in this case, it becomes much harder to define an elbow. So in this case, maybe you could even say, you know what? There are no clear clusters in my data, so I'll just choose maybe 3 or 4, and then I will stick to that. And you can see the data set over here. I forgot to tell you. So in this data set, there's more or less obviously 3 clusters here. One is here, one is here, and one is here. And in this case, not so much. Maybe 2 clusters, maybe one big one here and one here. Maybe 4, 1, 2, 3, 4. It's hard to say. But it's one way. By building this plot here, it's one way for you to determine that if you want.